So, good morning. So, we will continue with the lectures on introduction to optimization. So, in yesterday's class we looked at the morphology, anatomy and stuff like that of design, what are the various activities involved in a typical engineering process of an undertaking and so on. Now, we will get a little more specific and slowly we will begin to insert math into the course. After some time it will be just applied maths. So, we will solve a lot of problems, but all these problems will be concerned with energy systems, okay, or thermal systems. So, what is the difference between engineering design and analysis? I think at this stage it is important to recognize the differences between design and analysis. Analysis problem is basically concerned with determining the behavior of an existing system or a trial system that is being designed for a given task, okay. Let us look at an example. So, what is this? I have drawn on the board. I think people can take down, people who came late. As I keep talking, you can take this down. This is basically essentially a steam condenser. On the shell side you have steam entering, then it condenses and hot water comes out. As you know, this will be an isothermal process as far as the steam on the shell side is concerned. So, this condensation is accomplished by sending cooling water. The cooling water will enter at a temperature of Tc in and will go at a temperature of Tc out. So, its temperature will increase. This is basically called the Tx diagram of the heat exchanger. So, it does not matter whether it is a parallel flow or a counter flow, because one of the fluids is changing phase, okay. This problem, there are several ways of working this problem out. One possibility is I want to condense m kg of steam which is at a particular temperature and pressure into m kg of water, okay, right. Now I have cooling water at 30 degrees or 40 degrees centigrade. Now I want to come up with the design of a steam condenser. So, how will you go about designing this? Energy balance alone is enough? Is energy balance alone enough? Okay, what are the equations? What are the equations? mCp delta T of cold will be equal to this is m water, correct. This is just energy balance. With energy balance you cannot design a heat exchanger. Are you getting the point? So, that is the limitation of thermodynamics. Thermodynamics will tell you what are the temperatures, what are the resultant temperatures and how much of heat will be transferred eventually between the hot fluid and cold fluid. But thermodynamics does not tell you what is the area of the heat exchanger which is required for accomplishing this task, okay. That is why you study thermodynamics first, then you study fluid mechanics and then you study heat transfer and then you study optimization. You have chosen to study optimization now, okay. Is it enough to design the heat exchanger, for example? What do you want to find out? I want to tell you the design solution will be how many tubes are required in a shell and tube heat exchanger, what should be the size of the shell, what should be the diameter of the shell, whether you will have a U tube kind of situation where it has several passes. For example, will everything go like this or will it go like this? Accordingly the diameter will get reduced and so on. So, there is a issue of surface area, how much surface area is required for accomplishing this. What is the equation for this? What is this? This is basically the Q of the heat exchanger, right. It is called the heat duty of the heat exchanger. This Q will also be equal to This Q will also be equal to UA LMTD, where LMTD is the logarithmic mean temperature difference. U is the overall heat transfer coefficient, A is the area available for the heat exchanger, area of the heat exchanger, which is directly related to its cost. Okay. So the analysis problem is, watch very carefully, the analysis problem is like this. I already have a priori some heat exchanger available, some condenser available with me, right. I want to study its thermal performance. So for the analysis problem, I either have a new heat exchanger or either have a second hand heat exchanger, or I am getting it from web or somewhere, the details of the heat exchanger. Okay. Now I am going to see if this heat exchanger is used as a steam condenser for the following pressure and so temperature, what will be the thermal performance? What do I mean by the thermal performance? What will be the temperature rise of the cold water, for example? That is one thing which so that is basically analysis. There is nothing like design. I am not trying to come up with the design of an equipment. So this is the analysis problem. UA is known. If UA is known, there is nothing to design. You don't design the outlet temperature. You analyze and find out what the outlet temperature is, but you design the area, how you want that area to be, whether it is a plate heat exchanger or you have decided it is a shell and tube heat exchanger, how many number of tubes, what type of tube, what will be thermal conductivity, heat transfer coefficient, how this heat transfer coefficient will vary with time. Why will the heat transfer coefficient vary with time? Scaling and which is called fouling. Because of that, there will be a build up of this biological matter and all these things, because of which the resistance to the heat transfer increases. The resistance to the heat transfer increases, the heat transfer coefficient will exponentially decay with time. Therefore, you may have a situation where you will have a H which is going like this. So design of heat exchangers or design of heat transfer equipment for life is not such a straightforward task. Suppose you want to design it for 15 years, you have to consider all this. There may be something like what is known as an asymptotic fouling factor. Eventually it will settle down to a fouling factor that can be obtained by doing calculations and so on. Are you getting this point? So design will involve all this. The straightforward problem which you have learned probably in ME 317, that is the heat transfer course. For other for MTech and PhD students, you have learned heat transfer elsewhere. Basically they will give you all the dimensions and you will have to work out. Okay. So sometimes it is very tricky because the LMTD is a logarithmic mean temperature difference. So you will have to go round in order to get that, right. So you have to use TDS iterations to get these temperatures. You do not realize the importance of what I am saying till you encounter quiz 1. Okay. So it involves TDS iterations, but of course all the equations are there, you can get, you do not have to put that much of a fight. You put a little bit of a fight, you will get the result. So this is the analysis problem. What is the design problem? You want to design a steam condenser for the 500 megawatt fast breeder reactor plant coming up in Kalpakkam. It is a practical problem. They are doing it now, right. In India will have the plant in the next 2-3 years. You will have a 500 megawatt plant or a 1000 megawatt plant, whatever. Now you know the conditions, the pressure and temperature of the steam. Okay. So you know, basically you know the temperature of the cooling water. You are going to get the cooling water from the sea. Okay. So how do you go about designing this? Can you take water at 30 degrees and send it out at 80 degrees? What is the problem? Thermal pollution. So there is a limit, there is a cap on the maximum delta T which is allowed. What is that value? 5 degrees. It is about 5 degrees. Otherwise the green activists will cry. Okay. Even otherwise it severely disturbs aquatic life if the delta T is more than 5 degrees. So a constraint is already coming up in your design. Okay, there is a 5 degrees, you are allowed only 5 degrees. Of course the sky is the limit, you can have an infinite flow rate. What will be the size of the pump? Okay, you can have a beautiful, wonderfully green design. Delta T is only 1 degree centigrade, but what will be the size of the equipment? Heat transfer equipment work best when there is a temperature difference. So I want more temperature difference, but some fellows are saying only 5 degrees allowed. So there is a constraint which is coming on me. Okay, and there is a constraint coming in the form of losses. The power required for the pump should not be more than the output of the 500 megawatt plant. It won't happen. I mean, if you come up with some silly design, you come with the most fantastic fluid mechanics solution and then come out with that, what is the use? You go home with negative power. Okay. Now, are there more constraints? Of course, yes. The salt water will corrode, man. The salt water will corrode normal steel. So you have to go for stainless steel, or in fact even titanium. Titanium, the cost is 2,500 rupees a kilogram. Stainless steel about 80 to 100 rupees. So what innocuously started was very harmless, MCP delta T hot equal to MCP delta T cold, Q is equal to UA LMT. Now you are stuck with so many things. Now there will be a engineering manager, there will be engineers, and then they will do analysis, then they work out cost. So the design is going to be an extremely cumbersome affair because of the various constraints which are built in. Okay. So the design problem is m dot steam fixed, Tp is fixed, that is the enthalpy is fixed. So you know what is the HFG, so Q known. For the given Q, what will be the size of the equipment? That is the design problem. For a given U and A, what is Q is the analysis problem. The Q is not known a priori in the analysis problem. The Q is known to begin with in the design problem. So a simple problem like this, we can branch out into design and analysis. But originally when people try to design, leave this heat exchanger, other equipment, they will usually follow a nomogram or a data book. There will be some data book. So for this much load, this should be the thickness, this should be the diameter of the shaft, and they will have a factor of safety and do all this. So analysis was divorced from design. But now we have got lot of finite element analysis tools and all this. Therefore analysis is becoming an integral part of design. The idea behind that is alternative designs can be analyzed and you can find out whether the stresses are okay, and without having to build new prototypes on the computer itself, using simulations you can study the performance and choose the best. Okay. So this is essentially the difference between analysis and design. The sizes and configurations of the various parts are known a priori. For which problem? For the analysis problem. On the other hand, the design problem is to calculate the sizes and shapes of the various parts of the system to meet performance requirements. So whatever I have written in PowerPoint there, it is much better explained when I do it on the blackboard, right. So through the example. So the determination of the behavior of the system implies the calculations of its response under the specified inputs. For example, this system, suppose I change the U, suppose I change the A, or in this system I just change the m dot, what happens? Okay. From the design flow rate of steam, minus 10%, minus 15%, plus 10%, plus 15%, what happens? So you will have to do what is called a sensitivity study also. So design of a system is essentially a trial and error procedure. You will start with some sizes. You are going to do it in today's class. We will start with a simple problem. You will select a bunch of components and then you will assemble them together, that becomes a system. Then you will use all the equations known to you and see whether the system is working. If the system is working, it is a feasible or an acceptable design. If it is not working, you will turn around and then try to change some of these components or some of these parameters, and you will keep on doing it till you have an acceptable or a feasible design. Okay. This is how the design procedure is done. If the trial design does not work, we need to rework to come up with an acceptable system. in both these cases we must have the capacity or the ability to analyze designs to make further decisions. Therefore, I make a submission that analysis thus has to be embedded in the design process, it has to be integral with the design process. Design and analysis are two sides of the same coin, okay. So we should not simply do a design based on some data book or based on some thumb rules or formula and so on. Of course, for a silly problem like what is the size of the pump required for your apartment or something, you do not have to do complicated finite element analysis and all that. You go to your plumber, will say sir 5 HP pump will work, but there he is not talking about optimum, but there we are trying to choose something which works, that is okay, because it is not such a costly equipment that it really matters. But my assignment number 2 will make you realize that all these things also matter, even for a pump and a piping system for an apartment. It pays to check your numbers properly so that you come with an optimum design. Okay. Now we will go to design of a workable system. So in yesterday's class we already saw that there are several possible solutions to a design problem, but all solutions are not equally desirable. Some solutions are better than others, whether it is better or not, how some solutions are better than others depends upon the objective function and depends on the analyst, depends on the user what he wants to call as desirable or not. Actually when an objective function criterion is defined, it could be cost, weight, heat transfer to pumping power, specific fuel consumption, whatever, invariably there will be only one solution which will be an optimum. So the goal of this course is to help you identify the optimum in certain situations, but because it is a classroom environment I will restrict the number of variables to 2 and 3. If you encounter an optimization problem where there are 2 or 3 variables, how do you go about searching for the global optimum? That is a goal, that is the intent of this course. Once you know how to do it for 2 or 3 variables, it is possible for you to write a program or use some package and then extend it to any number of variables, okay. Sometimes the optimum may not exist, that is fine, because sometimes the optimum will be infeasible, sometimes the constraints themselves will fix the solution and so on. All these things we will look into as we progress along. So therefore, just like there exists a difference between design and analysis, there is a certain difference between a workable system and an optimum system. An optimum system is necessarily a workable system, but a workable system need not necessarily be a optimum system. Is it okay? We are not making fun of the workable system. I am not making fun of the plumber, okay. So after all he gives you a pump which works, okay. For many of us do not even know what the ratings are. How many of you know what is the rating of the compressor in your refrigerator? What will be the approximate power consumption of the refrigerator? 100 watts, 150 watts, we do not mind at all. So if that is why the Samsung or LG will not advertise, we have come up with a new refrigerator which reduces consumption by 10%, we do not really care. But if somebody says I have come out with an air conditioner which has got a 10% reduction, we will go and buy, because air conditioner the power consumption is more, and then over a 5-year period it will amount to lot of money, lot of savings. However, nowadays we have the star ratings in India, right? There is something called the Bureau of Energy Efficiency, they put for 1 star, 2 star, 3 star, 4 star. So 5 star is very efficient. So only first you have to get accredited and then they will give you a star rating, that gives you the economy, okay, economy in terms of power consumption. So a workable system is definitely preferable over a non-workable system. So a workable system is infinitely superior to something which is beautifully designed but does not work, okay. So first is we have to make something work, and then we go to the optimization. Furthermore, the cost of engineering time, human resource, effort, computer systems and the software associated which are required to optimize large systems may not warrant the use of additional efforts to progress towards an optimum system. So there may be cases where you know it is underperforming, but you are prepared to live with it, okay, chalta, it is fine. So this is not such a serious problem, but you can't do this when you are having a 500 megawatt plant, okay, when you are trying to design an Airbus 380 or a Boeing 777, or now the Boeing 787 Dreamliner is having a lot of plastic, you know, they are trying to reduce the amount of aluminium. Now the long distance flights, the Boeing 747 had 4 engines, it was a great guzzler, it used to consume so much of fuel. Now the 777 it's got only two engines. So there continuously people are it has got only 2 engines, but it has got an auxiliary backup. Invariably if the engines fail, it's basically the starting issue, the starting circuits which fail, so they have a redundancy on that, okay. And there is something called, I am totally diverting from the topic, it's okay, we can cut it later. So, but still all these things have to follow what is called ETOPS. I am now deviating from optimization, I am live on air, so all these things have to satisfy what is called the ETOPS, ETOPS, extended twin engine operating performance standards, ETOPS. So if a twin engine has to fly between 2 cities, it should be within 180 minutes of the nearest airport on which it can land, okay. So if it is a 2 engine, they will not allow you to fly completely over the ocean for 8 hours or 9 hours. So even the 777, the 777 which is the latest, is subjected to the ETOPS standards, but a 4 engine jet, Boeing 747, the jumbo, is not subjected to that because it has got 4 engines. But now the twin engine itself is infinitely superior because it has got terrific fuel efficiency and so on. So it is subjected to the ETOPS, but it has gone on a 21,000 kilometer, it has flown. The Boeing 777 has flown 21,000 kilometer with 53 pilots and so many crew members. This was the test flight, but now the maximum they are operating is about 14,000 or 15,000 kilometers, okay. So we will cut that. Right, now the system simulation is going to come in the next class. Now we are going to design, you guys are going to design a workable system. Problem number 1, you can put the title as design of a workable system, problem number 1, okay. Select the pump and piping, for a system to convey, select the pipe, did I say pump and piping or? Okay. Select the pump and piping for a system to convey 4 kilograms per second of water, okay. The first data is select the pump and piping for a system to convey 4 kgs of water from one location to another, 250 meters away. So length is 250 meters, comma 10 meters higher than the original position. Okay. So a depiction is given here. There is a sump, there is a overhead tank, you are taking water from here to here. So this is the pipe, so your M is 4 kg per second. The height difference is 10 meters and this L is 250 meters, okay. It may be an apartment complex, whatever. 4 bends exist along the pipeline. The head loss in a bend is given by H equal to K V squared by 2G, where K equal to 0.15. The friction factor for turbulent flow is given by .182 Reynolds the minus 0.2, 0.182 Reynolds the minus 0.2. properties of water are rho equals, yeah, feel confident, okay, 1000 kilogram or 9000 kilogram per meter cube, mu okay. Okay. Go ahead and give me a proposal. There are two things, you have to get the pump rating, the diameter of the pipe, length of the pipe is given to you. So, it is a design problem, it is open ended, people are not giving everything and asking you to find what is the total head loss, that will be fluid mechanics. This is design, okay. Please go ahead. So, how much is it in millimeter? 25.4 into 1.5, 38, 38, we can take it as 38 millimeter. Okay. So, yeah, tell me the velocity. What is the velocity, Anand? 1.97 meters per second, is it correct? Huh? 2 inches, no. 3.53? First calculate the Reynolds number. Reynolds number is equal to correct, Reynolds number correct. So, why am I writing the same thing in different ways? This is the engineering definition of Reynolds number. No need to go through the intermediate step of determining the velocity. However, you will get Rg because unless you calculate the velocity, you won't know whether it is laminar or turbulent. Okay, anyway, you are anyway calculating the Reynolds number. So, this 4m by pi d mu is basically used by practicing engineers. Okay, fine. What is the Reynolds number? 1.7 into 10 the 5. Okay. Is it turbulent? Is it turbulent or not? Yes. What is the limit? 2300. Don't get confused. 5 into 10 to the power of 5 is for flat plate. Okay. So, the use of the correlation is safe. We are allowed to use a correlation. Therefore, the friction factor is whatever you do, it will be 0.01, 0.02, 0.03, it will be like that, right. If you get 1, 2, 3, then you go back and check, it will be 0.0 something. How much is it here? 0.0? 0.018, good. Okay. Delta P is head loss HL rho G. Okay. So, this is basically FL V squared by 2 GD into rho into G. F is known, L is 250 meters, velocity is known, D is known, rather assume, go ahead and calculate this. I got 0.18, does not matter. Or you can keep it as head loss itself, you can keep it as head loss and add the other heads, does not matter. How much is it? $73.8 what? It cannot be meters. This is meters. Huh? This is 73.8. Head loss is 73 point. Is it fine? Okay. Now, I will erase this portion of the board. Now, add total head loss is 73.8 plus 10 plus how much is this? 4 bends 4 K V squared by 2G. How much was that? 0.38 meters, na? Huh? Total head loss is 73.8 is correct. I got 67. What happened? I got 60. Can we? What is the correct answer? 67. This one. 60. 67. Okay. 77. Now go ahead and calculate the power. How do you calculate the power? Huh?
Head into flow rate.
Head into
Flow rate.
yeah. So what is a is it okay? It will be q delta p, right? It will be q delta p, meter cube per second into Newton per meter square, Newton meter per second, joule per second will be watt. Eta, no pump will work at 100% efficiency, therefore eta has to come in the denominator. Okay? If you do that, reasonable efficiency for turbo machinery, reasonable. Okay. Therefore, power equal to how much was it? 3.5 kilowatts. How much was it? 3.7 kilowatt. So you go to the market, buy a 5 HP pump, okay, go to the market and buy a 1.5 inch pipe, call your plumber and fix it up and switch it on, it will work. So at the end of today's class, you have learned how to design a simple pump and piping system for a domestic application and so on. As somebody said already, as he rightly said, this is not the optimum design. Maybe the 1 inch pipe, maybe the 1 inch pipe will have less, the 1 inch pipe will have less cost. But as the diameter decreases, what happens to the pressure drop? Because the velocity increases and so on. So, so there will be a complex interplay between all these 3 parameters. Okay, as I told you earlier, we will look at it on the next class. Next class will be I will look at some. Let us develop on this. Let us develop on this idea of a simple system consisting of 2 components of a pump and piping, and let us see how we can proceed to the optimum solution of this system.